Okay, let's start with this presentation. First of all, I want to thank ReversingLabs and Nebula for this opportunity to present our work on how we used graph database in our system. My name is Goran Cvijanovic, and I am a software architect in ReversingLabs, and I will present today how we use the graph database in our explainable threat intelligence system. And for a start, I will tell a little bit about myself. I'm a software engineer for more than 25 years of experience in IT, dealing mostly with open source databases, integrations and optimizations, more than 20 years in database systems. Started with relational databases and mainstream databases like Oracle and Microsoft. Later switched to open source databases, and also some NoSQL databases in later years. After that, I will present a little bit, tell about ReversingLabs. ReversingLabs is a leader in cloud delivery object security systems, addressing the latest attacks, advanced present threats, and polymorphic malware. So all types of malware software. The ReversingLabs Titanium hybrid cloud platform delivers automated static analysis and file reputation services that represent the fastest and most accurate insights of the file structures and content in the industry. Because of that and our specific technology, we have explainable threat intelligence for any file, any location, any threat. So all the information we have about files and the systems are covered by our technology. Titanium platform, the machine learning hybrid cloud platform that harvests thousands of file types at scale and speed, that threat detection through machine learning, binary analysis, and continuously monitor an index of over 10 billion files for future threats. Titanium Scale is a workhorse and is capable to process over 400 file formats and 4,000 file types identified from diverse platforms, applications, and malware families. Real-time data inspection of files, scalable up to 100 millions of files per day without dynamic execution. So files are unpacked and they are forming a hierarchy between them, so we know the dependencies between files, and those dependencies are candidates for potential use of graph database to analyze the relations between files. And I will present some use cases we thought that can be covered with graph structures and graph databases. We are processing that use cases in our production systems and standard database systems, but try to optimize in a way of better performance or more capable systems like graph databases, which are available today. One of the use cases is availability of files for download. So our users are interested in downloading files available from our systems. Some of those files are just for some customers, so they are private files, and there should be security enforcement in that downloads, and the other one are publicly available, so they can be exchanged in community or with our partners and users. The other use case is access control list for file download services. So they are role-based, and our users have to be able to download files on a secure way. And third use case we covered with and tried to cover with the graph database solution is malware status propagation in reputation service. So we are unpacking files and detect that something is malicious in that archive, and we would like to be able to propagate that malicious to the container which contains that file. And because of the many files are existing in a different containers, in a different archives, those propagations have to be on all the archives, so and that form a graph system by nature. And the other one is same for goodwill reputation. If we have a trusted archive and some file which is contained in that archive is somehow suspicious or whatever, then that goodwill reputation can override that, and that also forms one type of the graph as a structure. Some numbers and volume we are dealing with. We have around 28 billion metadata records about files. Around 10 billion files are available with a security status classification. About 6 billion of that files are available for download from our storage systems. It is around 6 petabytes in size, and it forms about 330 billion relations between files. It is a huge graph system or relation connections between files. About 8 million files are processed each day, so they form about 10 times more interconnections between them. So it's continuously increased that number of relations between files in our system. So first of all, we tried to set up test cluster for testing graph database system. It consists of 6 nodes, bare metal, with performant machines with 64 cores, 256 GB of RAM, and 21 terabytes NVMe disks per machine. And those database graph cluster is built with a replication. It depends on the graph database system, which type of consistency they are using, but usually we deal with 3 replicas in a system. Goals we have are very simple. We would like to have a system which will be able to handle historical data load of 30 billion vertices and 300 billion edges. which is relatively a big data set. And a simple requirement is to be able to query relations between the parents and children of the specific file vertex. And yeah, that's the very simple requirement we set for the start. Cluster setup with the Nebula graph. Nebula graph is open source system, so we downloaded the installation from GitHub. In our system we are using Linux and CentOS 7 as OS, and we just installed from RPM and modify some configurations according to cluster configuration. And after that we just tested if we are able to connect to the database and check the internal structures if they are working correctly. Some configuration parameters for graph database. We based our system on 1.2.1 Nebula database version, which we considered mature in that moment. After that, 2.0 was released, and we decided also to adjust some parameters for ports which are used for specific on each node, and we adjusted that to those ports used in 2.0 because of the future updates we are expecting to do to switch to new version, to upgrade Nebula cluster, and our software which will be connected to that cluster doesn't need to change ports or any specific parameterization, except switch to new cluster if we decided to change name or something. We also adjusted some draft timeouts according to recommendations from Nebula, and heartbeat is adjusted to 40 seconds and timeouts to 2 seconds. Nebula graph is based on RocksDB as a key value store beneath, and we also adjusted some batch size and block cache according to our memory on a cluster on the nodes. We also have experience in our system that LZ4 compression is the best option for us, so we adjusted also that. Some other parameters are also adjustable. RocksDB is very popular database platform for key value store, and there is a lot of recommendations on internet and directly from RocksDB how to tune some parameters. There's actually 3 layers. One is on the database options layer, then column family layer, and block-based table properties. So we adjusted that according to some recommendations, and do some tests internally, and performance was quite okay. So after we have operational cluster, we started with the data model and prepared the data model according to our use cases. Modeling in graph databases is actually very natural for some engineer who is thinking about structures in a system, and vertices and edges are representing values, attributes of some tables, and relations are directly represented by the edges. In Nebula, we are dealing with the vertices and the tags, which is actually group of properties which is combined together as a record, and edge types and edges, which are connections between vertices. We have here some groups which represent group of tags, and the sample is representing the attributes connected to the files. And we also have user vertices and source vertices. User are actually users of the system, and sources are represented by domain from which the file is received or is connected somehow. For tags, we have here some attributes about information, main information for the file. Files are represented with the SHA-1 hash representing the file itself. We have record timestamp, is the time when we receive that file, and some other attributes like type, so it's file type, size, storage, relation, and some specific to our technology is RCA2 information about classification and some dates and timestamps, and some additional metadata about reason and results and factor of threat level of that malicious samples or files. Users have that internal tags as a username and representative if those attribute for privacy, and with that organization and model we will be able to query that data set and fulfill our requirements. So after that model and creation of the objects in a graph space, we need to start with the data load. There is two actual groups of data load. One is history data load. So we need to be able to load our historical data or synchronize our existing databases with the graph database. And the second one is real-time data synchronizers, which will keep those related data sets or related databases, for example our production database with our graph database in sync. For the first part, for history load, we tested the proprietary, it is actually open source software developed by Nebula graph engineers. It's called Nebula Importer, and it's shown that it is capable enough and can be tuned to fulfill our requirements, and speed of the load, data load, is quite okay. It is tunable. We can tune concurrency, how many parallel workers we can have. We use the CSV files as a source, and also we can tune batch size. When we insert the record by record, it can be relatively slow, but if we insert in the batches, then we can increase the throughput. So the combination of concurrency and batch size impact the throughput, but also if we push too much, then the latency will increase. So we need to find a fine spot which will be balanced between increased latency and data load. So the throughput will be at the maximum speed. And these are some numbers we used, and those numbers show that maximum throughput for us. Load is taking for hundreds of billions of records. It takes days, of course, to load it in a relatively small cluster of 6 nodes. For real-time data sync, we use our internally developed Python loaders based on the Nebula Python driver. And we are synchronizing data from production database systems through the Kafka streaming or Kafka queues, and loaded that to Nebula database. It is a real-time system, so it is actually a data synchronizer. So after we loaded the complete data set and activated synchronizers, then we got the operational system in sync with our production data. I will not talk much about all the processes and workflows we set up, but I will pinpoint some interesting stuff we found during our implementation. So one of that is when you have a lot of vertices, like 30 billion we have, and you have Nebula version 1, which using for vertices 60-bit integer as ID, then you can expect collisions. So that's one issue you can have when you deal with a lot of data. So anyhow, we detected some collisions in our system. IDs are generated with a hash function for Nebula graph. It is a Mu2 type of hash, and we, for our volume of data, generate hash from SHA-1 string, and got about, for today we have 10 collisions. So it is not a large number, but you need to find a way to deal with collisions. And we decided to implement that through collision detection system, which is based on external data set in our production database. So we are able to detect that we have collision. And collision mapping, we developed in a way to implement that as edge on directly in Nebula database. So we have edge named collision and 2 indexes over that, and we are able to query directly from graph database collision mappings. What it means, when you insert some data, some vertices based on SHA-1 hash you have, then you are able to insert both of those hashes, which will, without collision detection system, will finish as the same vertex ID in a graph database. In this way, we can have separate vertex IDs for those 2 samples. Here is representing how it is as a result from query in a Nebula graph database. Because of indexes which are existing in a Nebula graph, we are able to look up collision and get a collision list directly from graph database using where condition over the collision level. So it is actually a small trick how to be able to query and get all the collisions in a system. So after we have all data in sync and collision resolution, we are ready to start with some queries, but before that we would like to have backup of our database. So if something goes wrong during the queries and data synchronization in real time, we spend a lot of time to prepare all the cluster and load the historical data. So the idea is to have backup of that. Nebula graph offers the snapshot mechanism, which creates snapshots on each node in the cluster, and after that you can back up your data to some external storage or some other external system, which will you can use later for restore or some migration or whatever you will need your data. Backup and restore we did with using open source product rclone, and using bash scripts to copy data from snapshots to external storage. It is easy to implement, and it is natural for Linux systems. And then after all that, we are ready to do some tests with the queries for our use cases. One interesting thing about NoSQL and graph databases is that sometimes it is hard to figure out which data you are actually inserting, because it is based on a hash and IDs, and usually those systems need additional indexes to be able to query data using where conditions or some other syntax available in the system. And in a Nebula graph, we created record timestamp index, which enables us to fetch records in specific time periods. So if you need information which records are entered the system in specific time, it is very good information to validate if everything is okay between your production system or data you have in external systems, and compare that to data in graph database. And here is an example of the syntax for lookup, fetch, and yield. Everything can be found in Nebula documentation. It is very descriptive syntax, and it is effective. So connecting those parts with the pipes, that's how it is implemented is Nebula graph. And you can get, for example, here all the records which are inserted in 15 minutes ago in specific seconds. So if you have a large throughput, then you will get a few hundred or something records each second entering the database, and you can compare that to some production external system and be sure that all the records are in sync. This is an example of the result of that query. So we got information about attributes, and we can compare that to source where those records came from, and we can see that all data are in sync. And the other type of queries we can use are statistics for ownership, for example. So you remember those use cases I mentioned earlier. If we fetch statistics for file ownership, we can easily validate if we, for that specific hash, SHA-1, we are using here, do we have and how many private and public sources. So here you can see that for some popular file, we have here 32 and 24 private and public sources. What that mean? That means that we received many times the same file, or we received some archive which contained that file, and when we unpack that file, it will be available as a new source in our system. And form, of course, relation and hierarchy in a graph database. The other type of statistics is statistics with relations, and that hierarchy, direct hierarchy or between the files, and we are able to use union all functionality in graph database to combine, for example, children and parent relations in one response. There is also feature that you can specify that Go command will expand through the graph in both directions, but that will be both directions for each vertex they touch in a system, so it can explode if you touch some hot vertex with many relations. And in this way, with the union all, you are going just one way, and it is more efficient and prevent the transversals through the graph to explode in too many relations. And yeah, the result of that query with the statistics is so we have some kind of analytical response. It is a type of the relation. We have here is just two levels because this sample doesn't have children, but we got a result for sample and parents, which are with a different classification. So we can count how many in hierarchy we have suspicious, malicious, goodware, unclassified files. And you can see that this specific file have many relations, more than 3,500,000. So 350 or something thousand relations. And the response time for that query is actually good. It is 1.4 seconds, and it goes through all that relations, so hundreds of thousands of relations. And yeah, I put the note here. Yeah, it's 1.4 seconds. You can read everywhere that Nebula graph is have a high performance system, and it is actually usually in response times is in milliseconds, maybe tens of milliseconds, but we got 1.4 seconds. So with the relational part which have many vertices and edges, you can expect slower response time. But yeah, hey, it's query over 30 billion vertices and 300 billion edges on 6 nodes cluster. So what you can expect. And yeah, you can do some tricks, of course. Statistics for relations with union all and random filter. What that mean? We maybe don't need all these hundreds of thousands relations. We need just statistics which will be for some part of that relations, but how to achieve that? There is no way to stop on some point to filter something, so we can do some tricks, and that trick can be random number generator, which will be dynamically executed during the query, and this is the case. So we put in a where that we will filter only generate random numbers 0 to 4, 0 to 3. It's actually 4 random numbers, and we will take 1/4 of complete data set. That's what we can expect if we're lucky. And will this do the trick? Speed up queries maybe, or the system will goes through all the relations again. Yeah, we don't need all the results, that 100,000. We need just subset to see if we have enough, if we have different classifications in our hierarchy. And we got this as an answer. So yeah, it's 5 times, no, it is 3 times, around 3 times and something faster than executing on whole data set. Yeah, the answer is yes. It is less expensive to do some filtering than fetch actual data from disk. And we are covered here with all the types of classification. So subset is giving us enough information to be able to proceed with that result. It is interesting that we can do some tricks here and speed up the queries, especially with the vertices and the graphs with a lot of vertices and interconnections. And as a final part, I will note some challenges we have during our implementation. One of them is data set. So when you have nodes with tens of millions of relations, it is huge amount of data to parse, to query, and the query execution time sometimes can crash graph D service of Nebula graph. So it is actually engine which executes the query, so it can be using all the memory or be unable to process all the data, so it can crash in some situations. If you have more than one graph service, then you are on the safe side, I would say. And also if you have some watchdog which will respond that process back again, it will be back in the cluster, so you will be able to query again. It will be in sync with the metadata service in Nebula, and will be able to execute query again. The second one is some operational challenges we have, handling the node downtime. So when something is broken, or some part of the system on one node, some service is down or unavailable in a way, query will got errors, and we need to restart graph service to be able to execute that query again against all the nodes and storage services on Nebula graph. That is also challenging, and I am expecting that in that area Nebula graph will improve their services, and I know that in 2.0 and now on new 2.5 they did some improvements in that way. We are preparing to test also those new versions, and we'll see if some of the challenges are covered in the system. The other operational service is horizontal scale. You can add the new nodes and balance data. There is some situations when you need to stop your services because there is a small unavailability of the GraphD services because of metadata change, and it is not automatically synced, but that's the also area for improvement, and I think that the Nebula engineers are working on that already. In 2.5 should be a little bit better, and there is no support for vertical scaling. So if you add new disks in your system, then existing space cannot expand on that storage. The new objects which will be created will use that storage, that's true, but there is no option for now to expand the existing data sets to the new disks in existing nodes. So only option is to horizontally scale for now. And database software upgrade is also a little bit problematic. On the same version, like version 1, some new patches are backward compatible, but to change to the new version, to version 2, there is a lot of changes, and you have to migrate in some way your data to the new cluster you prepared with the new version. And there is in the version 2 migration utilities for that, but it is not rolling upgrade, and data will be migrated, but the cluster will not be operational in that period of time. Okay, then that's it for my side. I hope that you found this understandable, and that you learned something, and some pinpoints I put here about our implementation can be useful for somebody who will try the Nebula graph and implement that in their system. Thank you. I will check now for some questions maybe we have.